January 19th edition of the Common Good Podcast. Good to see you all. Thanks for being with us today. It's Science Day around here where astrophysicist, pastor, author, birder, Paul Wallace, husband, friend, joins us out of Decatur. Paul, it's again snowing here in Minnesota. I know a couple weeks ago we talked and I told you, it's just, we apparently... we figured out the water from the sky problem around here, and it's coming down all the time in Minnesota. How are things there? How are things there from the skies of Decatur?
It's wet. It's drippy. It's about 50, maybe in the low 50s. So it's pretty warm here. But it's not going to change temperature much because it's so overcast and dark and damp out there. So I imagine it'll be kind of like this all day long. Maybe in the mid 50s here. It's really pretty warm.
And Dan, how are things there in West Michigan today?
Yeah, it's rainy and might turn into snow. We'll see.
You guys with your snow. People with your snow.
Good luck to you.
My 14-year-old just wants one good snow.
Yeah.
It's been since she was like 7 that we had a good snow, like 7 or 8. Like a really good one where you can really get out in it. It's dry and packable and all that. She's dying. She's like, I just need,
Well, here's hoping.
Well, Paul, as we've talked about many a time, the human experience on this earth of ours has been that what happens in the sky frames up how human beings live. We tell stories about it. I mean, it's kind of the big narrative of the whole thing. We make other stories, of course, we need to, but boy, from religion to philosophy to how you spend your days, where you live. I mean, so much of this stuff comes from these natural experiences. And so chatting about what's happening, way up in the sky when the clouds do finally clear, give me a moment where people are like, hey, what's happening up in the sky? And we know so many things. When we talked, over text about getting our program together today, it's like, which of these great stories about astronomy in the sky should we talk about to help people kind of, get there, have their science fix?
There were a lot. There's a lot, and so I just picked the 4 that immediately appealed to me the most. But we could have talked about one of a dozen different stories, easily.
That on any given day you could just have these great things to talk about. Well, let's start closest to us if we could. That this weekend, this Saturday, the new moon will be the closest since the Middle Ages.
Yeah, I got the date here. It's not the new moon. Now, the new moon, you know what the new moon is? You know what that means?
Opposite of the full moon?
Yeah, it means that the moon is in the same direction in the sky as the sun. So whenever we do get a solar eclipse, it's at new moon. Okay. The sun, every time the moon passes in front of passes in the direction of the sun, once every month. That's where the word month comes from. It's moon, month.
All right, hang on a second.
Already blowing our minds.
Yeah, reward of the day.
Yeah.
That's where month comes from. Is new moon.
In fact, I call them moonths all the time. It drives my friends, my family crazy.
Oh my gosh! Well, my family's about to be tormented by the same thing.
Totally.
So once a month, the moon passes really close to the sun in the sky, and occasionally it'll actually cover up the sun, and you get a solar eclipse. So it's when the moon is in the same direction in the sky as the sun. That happens once a month.
Okay, all right, and that's called the new.
That's called the new moon. Yep.
When it hits that spot.
Right. When it gets closest in the sky to the sun on that cycle, it's called the new moon. Yep.
And there's a new moon every, something like
29.5 days. It worked out.
5 days.
So that's pretty close to the average length of a month for us, right?
Well, yeah. Yes.
We just trade 1 or 2 days throughout the year and add a leap year to make it all work.
Yeah. So you end up getting like 12 and a half months, 12, roughly 13 months per year is what you end up actually getting. Between 12 and 13. Lunar calendars work that way, right? So like Ramadan, for example, is based on a lunar calendar. So they don't have Ramadan occurs every 12 lunar cycles, which is not exactly equal to 12 moons. So the calendar for Ramadan goes in and out of phase with our calendar slowly over time because of that. Yeah. So anyway,
for a
we have a
long
new.
now you might not know the history of calendars, but it must be then that the moon was the easier way or the more apparent way for people to keep track of things.
That's right. It was because the year was a little harder to nail down. Yeah.
Right.
Sure.
You would need a big like sundial situation or some marker to know exactly when the year.
Right. But the moon, you can just look at the moon.
Yeah.
And it's like, oh yeah, it's new moon again. So that happens regularly, So yeah, that was the original calendars were all lunar.
Boy, that is just see this is the kind of thing, friends, that when you listen to this podcast, watch this live stream, you just just chit-chatting with a friend a little later and you're like, hey, did you know?
But so sometimes the moon is a little bit closer and a little bit further.
Right.
And last time it was 10:30 CE or AD.
Yeah. Last time it was close. Last time it was this close was December 3rd, 10:30. Wow. According to our calendar that we use now. They didn't use our calendar exactly at that time, but according to our calendar, it was 12/3, 10:30, which is a while ago. It turns out.
Yeah. I guess in some measurements, it seems like it was a while ago. I was reading something about human evolution, and how human beings are modern evolutionary version of us, somewhere 50,000, maybe 7,500,000 years, somewhere in there. But really, the civilization as we know it, keeping track of things like with writing and so on, maybe 10,000 years.
Yeah, 10, 15 tops. Yeah.
And then, as we were talking on this podcast a while ago about, the age of the Earth and something, I think I was watching a documentary about Mount St. Helens blowing up. Like, now the rest of the Earth is, like millions of years. So, human beings have really only been here for this teeny amount of time in our current form. And then, of course, our own history just inside of that, which can feel like a long time ago. When we're talking about the moon being the closest, what is the next closest that was recent, and could, without this fantastic article, would anyone know that, like, hey, look at that moon? It really seems
you really wouldn't be able to tell with your unaided eye, because one reason is you can't even really see the new moon because it's in front of the sun. It rises and sets with the sun, and so you just can't even see it. But no, we would not know. We would not know. Even if it were visible, we would not be able to detect it with our unaided eye. No, we would not. It's just a really nice curiosity, though, because what happens is there's two things. There's two cycles that you need to watch. One is the cycle of the phases, which we've already talked about, the 29.5-day cycle of the phases. Okay.
Yep.
That's one cycle, but there's another one. The moon takes about 27.3 days to orbit the Earth. Not 29.5, 27.3. Okay. So it's a little quicker. Right?
Okay.
Now, the reason those are different. The reason those are different is it goes beyond the scope of this course, as I like to say.
Because we live in a simulation, and they just make up the rules.
I'll draw a nice picture for you if you take my astronomy class. But for now, just know that there's every 29.5 days you have a cycle of phases. And every 27.3 days you have a single orbit of the moon. Okay. So they don't match. All right.
Because we're also traveling around the sun? Something to do with that?
Yes, it has to do with that. It has to do exactly with that. Yes. So the point is that the moon's orbit is elliptical. Sometimes it's closer, sometimes it's further from us.
Yes. Okay.
So every now and again, a new moon will land right on top of the point where it's closest to us. Those two cycles fall on top of each other. They go in and out of phase with each other, but every now and again, a new moon will occur when the moon is super close to us at one of its nearest point on its 27.3 day orbit. Okay, so when that happens, you get this. You get the closest new moon since the Middle Ages. When those two things coincide.
Wow.
I guess I was assuming from the headline in the article that this is going to be like the moon is biggest in the sky come Saturday. That's the opposite of true.
No, it is the biggest in this. Well, no, it's not the biggest in the sky since the Middle Ages. Okay, that's a different question. It's the biggest in the sky at new moon since the Middle Ages.
So there's been a biggest full moon.
Right, right.
That's a different.
You've heard of, like once every few years, you see all these headlines about a super moon or something like that.
That's exactly what I was confused by. Yep. Okay.
Yeah, they call it a super moon when the same thing happens as this, but the moon is full instead of new. When the moon is at its closest point in its orbit to the Earth and it's full, that's what they call a super moon.
There it is. So a new moon isn't a new moon when we don't see the moon at all. Like you can't
exactly.
So this is the closest that the moon is going to be, and we can't see it.
This is the closest that it can be.
Can be in the new moon.
Pretty much. Yeah, and we can't see it.
All that, and you can't observe it.
You can't observe it, not with your eyes anyway, without burning them out, because at new moon the moon is essentially in the same direction in the sky as the sun. And these days I couldn't see it anyway because of the darn clouds.
So the sun's not shining on the moon in the same way because the moon is in between the sun and
right. Put it this way: the sun is shining on the other side of the moon.
On the back side.
It was
on the back of the moon. The dark half of the moon is facing us exactly.
Got it. Because there really is no dark side of the moon.
There is no dark side.
When we see these phases, are the phases not the same? Is the thing that makes a quarter moon, half moon, full moon? Isn't that the same? Aren't the phases the same thing? And aren't the phases caused by the rotation of the moon around the Earth? I mean, I know you said this was out of the scope of
by the motion of the moon around the Earth. Yes.
Okay.
Yes.
So phases and orbits are different.
Phases and orbits are not quite the same thing. They're close, but they're not quite the same thing because of the Earth's motion around the sun.
Got it.
Because the sun has to do with the sun affects the phases. The direction of the sun is important for the phases, but it's got nothing to do with the moon's orbit around the Earth.
Mm-hmm.
So
when you're teaching there at St. Agnes College, and you say to the people taking your course, okay, around here in this class, we're going to recognize that phases and orbits are not the same thing. But when you're talking to those anthropology students over there, that's the degree I had. When you talk to those anthropology students, it's the same thing. The orbit and phases, they're the same thing. But around here, we're a little more specific about that. Is that what we're talking about here?
What I want to know is what you have against anthropology students.
I don't. That's where I hung out, and I'm pretty sure that the people who knew the things that you knew were like, just don't get into the difference between
the students in Astronomy 101. They're English majors, they're anthropology majors, they're whatever majors. Yeah.
So you say to them, in this class, we're going to describe the difference between a phase and a
absolutely
orbit. But when you're in your when you're in your art class, your anthropology class, maybe your math class, okay, it's fair enough if someone just says something about is that how it is, that average ordinary people without the specificity of the things
right, exactly. I mean some things it's not worth being pedantic about in a context where it doesn't really make sense to bring that. I mean I could correct people if I wanted to, but I want to have friends, and
Okay.
Yeah.
All right. So,
Well, let's move
there
a
we
little
go.
further away from the moon. Let's talk about exoplanets.
Exoplanets.
They're trying to
Yeah.
figure out why there's this radius gap, like why we can see some smaller exoplanets and some very large exoplanets, but there's been this gap in the middle where we can't find any of this size. What's going
Yeah,
on
this is
here?
something that I didn't know about until I read this article. I didn't realize that this occurred. But basically, the situation is that 30 years ago, we didn't know that there were no planets around other stars that we know of. But now we have confirmed about 5,000 of them, with many more candidates yet to confirm. So they're common planets. It turns out, not surprisingly, astronomers suspected it all along. Planets are common. And so, what we do is we assume that other solar systems are like ours, because it's the only one that we have data on. When we started this investigation, but it turns out they're really not. In general, our solar system is a little different in some ways. In other words, there's a large variety of them. Okay, they don't all look basically like ours. But one thing that was discovered in looking at these planets is looking at their sizes, right? You sort of take all these planets, and you sort of classify them different ways. Their orbital, how long it takes for them to orbit their stars, how far away they are from their stars, how big they are. And it turns out that when you look at how big planets are, there's a bunch of planets 1.4 Earth radii and smaller. So in other words, there's a bunch of planets that are about 1.4 times the diameter of the Earth and smaller. And there's a bunch of planets that are about 2.4 times the size of the Earth and bigger. Okay. But there are very, very few planets that are between 1.4 and 2.4 Earth radii. There's a gap. There's a gap in the distribution there. There's relatively few of them. And it's marked. It's a very clear thing, and nobody. The question is, why is that?
Mm-hmm.
Why is it that I mean, in our solar system there are none either, right? The Earth and Venus are basically one time the same size, and then the next planet size up is Neptune, which is several times, 4 or 5 times the diameter of the Earth. So there's that gap does show up in our solar system as well. We have no planets in that region. So there's competing theories about it, and that's what this article was about what the competing theories are.
Wow.
One of them has to do with the fact that early in planet's life, in the life of a solar system, planets tend to orbit, sort of spiral down close to the sun, close to the star. And that's because there typically is a whole bunch of junk, a whole bunch of debris and dust and stuff like that in the disk of the solar system that that slows the planets down. As they slow down, they spiral in towards the sun and they heat up because of that. Okay. You with me so far?
Mm-hmm. Yeah.
Okay.
Yeah.
So the idea is that the smaller planets tend to lose more of their atmosphere than larger planets do, because they have less gravity, and so when the atmospheres heat up, they lose more of them. When you heat up a planet, like if we could take the Earth and heat it up,
as we're doing, yes.
Yeah, as we're doing, yes. It turns out, yes. If we continue on our current path, we will, and to a comical amount, if we just can really turn up the temperature of the Earth, we would lose our atmosphere fairly soon.
Sure.
Because the particles in the atmosphere will move fast enough to escape the gravity of the Earth. And so the thinking is that smaller planets lose their atmospheres more quickly and more of a larger fraction of their atmospheres, because their gravity is not as strong, whereas larger planets hold on to theirs. So planets that are smaller will lose more of their atmospheres and therefore lose mass.
I see.
And actually physically get smaller.
So they hit a point in their development when they're small, they're kind of safe. They hit a medium-sized point, and they get big really fast, or they
No, what would happen is
What's happening in those middle ones?
Like if you had a planet like Neptune and you brought it and you let it spiral into the Earth, spiral in slowly to the sun, it would lose a lot of its atmosphere fairly quickly because its gravity is not that strong.
Okay.
It's relatively small compared to Jupiter, whereas Jupiter has a stronger gravity and would hold on to more of its atmosphere.
Okay.
And so planets that are on Neptune size would get smaller because they're just gas balls, and when they lose atmosphere, they lose size. Isn't that weird? So
yeah,
that's one theory. Now there's a couple others, and one of the others I didn't quite understand had to do with collisions in the early solar system. But anyway, the article was about these competing theories, and I never really knew about that gap before, but it really is quite obvious when you look at the data. It sort of jumps out at you.
Yeah, it's weird that there is that gap, because you'd think it would there would be some sort of spectrum, and you would catch planets in the middle of this.
Right, and there would be
transition
just along this distribution of sizes, and it would be sort of. But there's not. It's what we call bimodal. There's a lot of small ones and a lot of big ones, but none in the middle.
The cosmic cookie cutter, as this article calls it.
Yeah. There you go. And just a reminder to people, because I had to remind myself when we started this conversation, that exoplanet just means a planet around some other star.
Right.
Unlike exoskeleton, which we talk about, which is like an outside body structure that you put on yourself. Because someone might read, if they were, or hear this and think, oh, exoskeleton, people are talking about a kind of planet that's like different, like it's just the shell of a planet or something like this.
Oh, right. No. Yeah.
It's just the language we use because we bias our own solar system. So we say around here, oh, these are planets. If they're from another solar, then we say those are exoplanets because they're not from around here. So the same kind of the added adjective that you put out that we put on things is what's happening here in astronomy, which is sort of an interesting human.
And the number just keeps going up. I mean, literally, I remember when I started teaching astronomy back in the late 90s, there were 1 or 2 exoplanets known. And now, literally, like I said, there's 5,000 that are confirmed, with many more thousand yet to be confirmed.
And how are we seeing these? Are we still, it's only when the exoplanet passes in front of its star that we can...
That's probably the most common way that we detect them, is when a planet basically we measure the light coming from a star, and as the planet eclipses the star, we get regular, steady, periodic dips in the brightness of the star. So we don't actually see the planet. What we see is the effect as the planet eclipses the star. Every orbit it passes in front of the star, and the overall brightness of the star drops because that little planet is absorbing some of the light between us and it. Yeah.
And so when there's a consistent dip, then they're like, okay, what's then happening is something is consistently orbiting that star.
Right.
So we know it's not just a space stuff. It's something.
So and those are actually kind of hard to detect not because it's hard to measure the light, but because you have to have a planet. We have to be basically in the plane of the orbit.
Right.
You know what I'm saying? I mean, it could be orbiting
so
face
what are
on
the
like
statistics of like...
Right. So it's a very tiny fraction of the total number of systems are actually eclipsing like that. But there are probably 5 or 6 or maybe more different methods of detecting them. That's just one of them, probably the most common way of detecting them. We've recently been able to get actual images of them. That has just started to happen in the last few years.
Is the James Webb, is that able to zoom in on an exoplanet yet, or?
Yeah, it's able to detect, actually take images of exoplanets.
Wow.
And that's really hard to do. I once heard a good description of it in one of my textbooks. It said basically it's like being 5 miles away from a street light and trying to take a picture of a bug flying, like a moth or flying around the street light.
Oh, I'm sure. Yeah, the speeds and the
Okay.
distances.
Yeah,
those-
and just the dimness of it, and the dimness of the moth right next to the bright light of the.
yeah.
That's the challenge: is picking the moth out from the glare of the street light itself.
When they're
Picking the
doing this,
planet out.
do they have an idea that okay, we think there's an exoplanet here.
Yeah,
Let's aim in this spot and
yeah. They wouldn't just pick a random star. They would pick one where they have a reason to suspect that there's already a planet.
gotcha. And the
And-
James
and-
Webb
Turns out they're right when they look. There it is.
the James Webb is changing the game for a lot of things though, huh? It's really, as this article says, upending our understanding of the early universe. Like we're having to re-examine a lot of things because of all this new data coming in, huh?
Yeah, let me tell you why James Webb is so good for seeing things that are early galaxies. Now, as we've talked about on this same podcast many times, the further you look back in space, the further back you're looking in time.
Yeah, and I know we keep talking
Right.
about that. And I'm just shaking my still. Okay.
So
yes.
Let me tell you this little bit here.
Just true.
Whether or not you believe it, Doug. Let me.
I believe it. I just don't understand it. Like most important things, I believe it and I don't understand it. That's all this is.
Back when at the moment of the Big Bang, back early in the super early universe, there was pretty much only hydrogen and helium. Okay, hydrogen and helium. A little bit of lithium maybe, but very, very little. So mostly hydrogen and helium. Okay, so the question you would ask is, you would say, well, where did all the carbon and oxygen and phosphorus and iron come from, and all the others? And the answer is they were sort of slow cooked inside of stars. That's what stars do. They're fusion machines. They build up heavier elements from smaller ones. And our sun right now is creating helium out of hydrogen. And one day we'll probably create carbon out of helium. So, but not today. Today is not that day. So the point is that over the course of the universe's lifetime, you get more and more and more what we call heavy elements. Astronomers, when they say heavy elements, they mean anything heavier than helium.
Which we all know is super light because it makes balloons float.
That's super light, yeah. So hydrogen and helium, number 1 and 2 on the periodic table. That's pretty much all we had at the get-go. But over time, stars have been cooking heavier elements in their cores. What this means is that if you look back into the early universe, you should see less and less oxygen and carbon, okay, and silicon, and iron.
Because it takes so much time to create these elements.
Right. And so there should be a gradual, steady increase of the amount of carbon, oxygen, and so forth, heavy elements in the universe over time. And now how do we know what a star is made of? How do we know what elements are located in a galaxy? What we do is we take the light and we break it into a spectrum. Okay, so if I want to know what's in the sun, I take sunlight and I put it through a spectrum and it makes a rainbow. Okay, and by looking at the details of that spectrum, you can tell what's in the sun.
Okay, so let's pause there. Why do these light waves and light particles, same thing, why do these particle waves, why do they represent what's in the makeup of the star?
So let me ask you this. Did you take chemistry in high school? I know you were an anthropology major, but did you take chemistry in high school or college or anything?
Yeah, probably.
Do you ever remember?
There was a room that had a periodic chart of the elements on the wall.
That's the one.
Some Bunsen burners. Yeah,
I was in there. In the
place. Burners. Yeah. Excellent. So,
Petri dishes.
Ever remember talking about energy levels or energy shells and hydrogen or any other? Does that ring any bells whatsoever?
It does not.
No, it does not.
Not at all.
Well,
Dan, do you remember this from chemistry? Energy levels?
No.
Shells,
Okay.
shell structure, 1s orbits, p orbits, d orbits, nothing like
No. I lost
Holy moly.
almost all of it. Yeah.
that. You don't use it, you lose it, right?
Yeah, maybe I forgot about it, or maybe my teacher forgot about it because it doesn't ring a bell at all.
Let me just put it to you this way. Every element has
Please.
its own internal structure.
Okay.
Okay. Now, don't worry about what that means. Just know that the structure inside a hydrogen atom is different than a helium atom. It's different than a lithium atom. And each one of these atoms, when they emit light, that light carries, in a sense, an imprint of that structure.
Oh, okay.
Okay, so that when you get the light from hydrogen and you spread it out, you can see some little dark lines in that. Basically, you have the rainbow, but imagine a rainbow with a few colors missing. You do this with hydrogen. There's a wavelength of red that's missing, a wavelength of cyan that's missing, and 2 purple wavelengths that are missing. And that's always hydrogen. Those missing colors are like a thumbprint of the atom. They identify the atom. Okay, and they're sort of a shadow of the structure of the internal structure of the atoms.
Okay.
So every atom's different. Every atom has a different structure. Every atom's spectrum is different because different colors are missing for different elements.
And when you're talking about light like this, is this more like radiation you're talking about versus the kind of light that we see from a bulb or from the sun or from the back of your iPhone?
No, it's the same thing. In physics talk, radiation and light are the same thing.
Because if someone looks at some hydrogen in a beaker, or helium in I don't know, coming out of a balloon, we don't see a bunch of light.
Oh, right. You got to heat it up.
If
you heat it up. So basically, if you take some hydrogen gas and put it in a tube and then run a high current through it, it'll light up, nice and pink colored. That's how we have that. That's all neon lights are. They have neon in those tubes.
Okay, well, there we go. Neon lights actually have something called neon in them. That
an
is,
element called neon.
Literally something I should have known.
Yeah, the original ones I think had neon in them, and that's why they're called neon lights. But they have different elements in them, and that's why they're different colors.
I can only imagine that Jim Eaton, who's commenting on the chat, is shaking his head like, you people, one of you didn't know that's what neon lights were. I just thought it was like some shorthand Greek for something,
Oh, no. The element neon, if you can find it on the right-hand side you go back into that chemistry classroom you're talking about and look 3 or 4 lines down on the right-hand side and you'll see a little Ne. That's neon.
Wow. So that's the energy structure that then's going to produce, if you heat that thing up.
Yeah.
All right. So
basically,
that helps.
Put it this way, every element has its own unique thumbprint.
Wow.
And you can see that thumbprint in that element spectrum.
Cool. Okay. Got it.
So
we're looking at.
Yeah, go ahead.
So what Webb can do that Hubble was not able to do nearly so well is to make spectra out of things. Okay, super faint things. In other words, what Webb can do that Hubble couldn't do as well is get spectra of these super duper distant galaxies. So we can split them up. We can take that light and we can spread it out and see what elements show up.
Wow.
And we fully expect to find no oxygen. And the further back we look, the less. In other words, we can test this idea by looking at galaxies further and further away. And as we do, we see less and less oxygen, less and less carbon, less and less iron. And by the time we get back to where Webb can see, we see nothing but hydrogen and helium. Because what we're seeing is looking back in time, and we're looking at the history of this history that we have long suspected is real, is being shown to be real, that over time we get more and more of the heavy elements as they get cooked inside stars slowly over billions of years. Isn't that cool?
It's so cool because the idea, one of the big questions a lot of people have in their understanding of how we got the stuff we have here is a designer, like a designer, architect, builder model where, look, someone made it, like most of the stuff we have around us. You're like, it didn't just happen here, right?
Yeah.
The old joke about like a turtle doesn't, if you find a turtle on a fence post, you know someone did it, right? Turtles don't get themselves up on a fence post. So people look around at all the things in the world, and they're like, well, something made all this. And then you get into a designer, architect, builder modality, and you assign that to God or, whatever. And then people come along, they're like, no, you don't need that designer. What you need is a certain set of conditions that then we can argue about what put those conditions in place. And then the system will create this stuff itself. So helium, hydrogen, just start cooking somehow, spinning around each other. And the next thing you know, you got a turtle on a fence post. Right? That everything gets...
there's a very important little like ... between hydrogen and helium, and then some things happen ...
and then someone put a turtle on, and then someone
one
put a
thing
turtle
led
on,
to another.
Put a turtle on a fence post. So all the things then you're suggesting that exist, everything we're looking at, moss and turtles and all the things that exist in the world, on our planet and the exoplanets, just happen because of whatever's produced out of the system that starts with hydrogen and helium heating up.
Yep.
That is just give yourself a minute.
And the truth is that if you ask, what is the universe made of, the answer is hydrogen. Still, it is predominantly hydrogen. This and in a fairly distant second is helium, and then after that, everything else is traces. So we're living like the world around us, our daily world. The elements that make up everything around us on this planet is really uncommon. It's in the sense of this is not in general what the universe is made of.
Mm-hmm.
The universe is basically hydrogen and helium, and everything else is like less than 1%.
And I know we're not in a biology online course here, but when people what caused the Earth to produce the things that the Earth has produced, that much of that has to do with the atmosphere, right? That an atmosphere gets created around the Earth, and then that starts to protect.
The atmosphere definitely made it
like
possible.
A petri dish.
Yeah, it protected the surface from harmful radiation from the sun, UV light, gamma rays, things like that. So that was definitely required. There's more is required than that, but that is definitely a requirement. You have to, and not just so we can breathe it. In fact, life began before there was oxygen in the atmosphere. Just not. It was not life as like turtles.
It was cells that start to. Yeah.
Right.
Oh, wow. Hey, what other things about, you said the issue here was that we believed, the people who study such things, look at me, we astronomers, we believed that, that the other universes, the other solar systems, would behave similarly to ours, which we have a certain understanding of. So then we said, well, there can't be a planet around that one because of whatever. What are the basic things that we thought the other solar systems were like, that's like ours, that turns out they're not actually like that? Like what's in the short list of that kind of thing?
The first thing is this. Well, the first thing you got to know is about our own solar system is that it's really kind of organized. I mean, you've got 4 inner planets that are relatively small and rocky. And then you have the asteroid belt, and then you have 4 outer planets, which are really large and made of this big balls of gas. Okay, there's a lot of differences between the inner and outer planets, but there's some structure there, and so that we say, okay, this might be normal for other solar systems, and I need to say it might be more normal than we think, but we're just not sure because here's what happened. when we first started looking for solar systems out there, first started finding planets around other stars, they looked nothing like our solar system. What they typically had, okay, were large planets on the order of Jupiter size that were super close to their stars, like closer than Mercury is to our sun. These planets were that close to their stars, orbiting very quickly. Okay. Known as hot, and the category is known as hot Jupiters. That's what they're called because they're hot. Isn't that good?
Oh,
Isn't that good?
that's also a club down in Daytona, Florida.
gonna say, sounds like a band
Florida
name.
I went to once. Yeah. Jupiter's had a great time there.
Yeah, this place has everything.
Yeah, hot Jupiters.
So funny.
Love it.
Hot Jupiters, yes, because they're hot because they're close to their stars, and they're Jupiters because they're so big.
Okay.
Which is nothing like our solar system, right? Nothing. Just not even close.
Opposite. Bizarre solar system.
But that turned out to be what we in the business call selection effect. Okay, selection effect means that because of the way we were searching for them,
yes,
for other solar systems, we were more likely to find certain kinds of them first.
Just a truth of the world right there. It applies not only to astronomy, but to every other field, right? The thing you're looking for, that's the thing you'll find first. Unless it's the thing you want.
The most obvious, the simplest example of a selection effect is when you look up at the sky at night and you think, oh, look at all those bright stars, the stars. But the truth is the stars you're seeing are not necessarily the brightest ones. There's a lot of stars in our field of view that are just too dim for us to see. Okay. And some of the stars that we see are not very bright at all, but they're close up. Okay.
Wow.
So we're not necessarily seeing the brightest stars. We just happen to see the ones that you see what I'm saying?
Yeah,
in other words, what we see with our eyes is not a random sample of stars. Put it that way.
Yeah, it's a different measurement. It's a different measurement. You're saying the thing we see the brightest does not describe the status of that thing.
Right.
That it therefore is the brightest. It just appears the brightest.
Right. It's like having it's like having a bunch of different light bulbs or different wattages spread out randomly. There's some that are dim that are close up that you can see, but some that are super bright that are way far away that are actually less bright than the dim ones. Because of the distance factor.
Nice.
So that's a selection effect, and that happened when we looked for solar systems because of the way we were looking for it. It was certain to find certain kinds of solar systems first.
Great.
And so we found those, and there turned out to be a lot of those. But over time, as we learn different ways of searching for solar systems and different ways for searching for these exoplanets, then we began to see a large distribution of kinds of solar systems. And our solar system is not. It's not like we found a bunch of them like ours. Ours just happens to be one of a distribution of different kinds that are out there.
When they're looking for life out there, are they believing we should look then in the solar systems that are structured closer to our solar system? Is that part of the deal? Is that part of the organizing of the looking?
Yeah, it's an assumption. And scientists are aware of this assumption that life, we feel like life, the first place we're looking are planets more or less like Earth, at a distance from their star where liquid water can exist. We're looking where we know we have one sample of life in the universe, and that's right here. And so our assumption looking out is that other life will be more or less like this. Of course, it could be wrong, but we've got to start somewhere.
Yeah.
And so that's what we do. We look for planets that are more or less the size of Earth and more or less the same distance, or a distance from their star, such that liquid water can exist.
How many solar systems are there roughly? What's the current guess count?
Right now, we know of, I would say, several thousand at least, 3,000-4,000 at least, something like that. But
Wow.
you have to understand that we're not looking everywhere. We're looking at a very tiny slice of the galaxy in a certain direction with a certain set of instruments. So you really have to multiply that out and assume that we're looking at a representative slice of the galaxy, and then multiply that out
by the number of galaxies.
So as far as the number of solar systems that we've detected, it's in the 3,000 or 4,000 range.
Wow.
But if you multiply it out, it gets very quickly up into the millions, billions. So, and that's just in our galaxy. That's just in the Milky Way. That's not
right.
Wow.
in other galaxies.
And that's just in our universe, and not even in the other universes.
And in the multiverse,
that we know actually exists. Yeah.
Well, speaking of other crazy things, in our last couple minutes here, there's this. I wish people on the podcast could see this image. It's from the James Webb Telescope, and it's these stellar spirals, and it's a binary star system. These two giant stars, but they're creating it looks like someone dropped a star in a pond, and it's creating these ripples outward. What's happening in this image, and how come we haven't been able to see stuff like this before?
Oh, we've seen other examples of this, but nothing quite so spectacular as this picture right here. And it does look like ripples, but what it actually is a spiral. Okay, so it's actually one long.
Wow. Okay.
It's a spiral. Okay, but you can't see that because the left half of it is cut off, and you can't see where the lines connect back on themselves. But it's a spiral.
Wow.
Yeah, isn't it cool? And so what we have here, it's really multiple star systems are super common, like double stars and triple stars and quads and things like that. In fact, if our sun is in the minority because it's an isolated star, most stars come in groups, 2, 3, or in larger clusters of several hundred or even millions. So this is a binary system, which that alone is not uncommon. But these two stars are both spectacular in some ways. One of them is about 30 times the mass of the sun, which is the upper limit of what you can have and still have a star be stable, hold together. So it's very large and very bright, burning its hydrogen fuel at an extremely high rate. Big stars like that don't live long. I mean, when I say live long, I don't mean 2 years. I mean a couple million years, something like that.
Okay.
Before they die out, as opposed to our sun, which was going to live 10 billion years.
Wow.
So
little engine.
Yeah, a little engine
that could.
So one of these stars is just a really bright, large, massive star on the very edge of what is what's possible physically to hold together. And all stars like our sun emit what's sort of, you call it a stellar wind of particles and so forth. And our atmosphere shields us from that. A bunch of protons, electrons, other particles, and intense radiation from the sun. It's called a solar wind, and it's just a steady outflow of particles and radiation from the sun. All stars do that. And this star, this really large star, the 30 solar mass star, has a lot of that wind, a lot of that dust and so forth coming off of it. The other star is known as a Wolf-Rayet star. It's a special category of star. And it has run out of hydrogen fuel. It's also very massive, probably started at about 20 solar masses. It has come to the end of its hydrogen burning phase. It has run out of gas. Okay. It's run out of hydrogen fuel. Okay.
Nice.
And so what happens in a star like this is that it, right before it dies, it kind of upshifts into burning helium. And that is an extremely energy producing situation. It basically, the brightness of the star doubles, triples, quadruples. It gets much brighter very quickly over a short amount of time. So it's burning helium. And what's happening with these, so they're both very intense stars with pushing out a lot of solar wind and so forth, but they're orbiting each other in a highly elliptical orbit. So by highly elliptical, I mean sometimes the two stars are super close and sometimes they're super far away.
There you go.
Okay. So when they orbit, one of them passes super close to the other, and their winds collide with each other. These flows of wind collide with each other when they're so close, and it basically creates this spiral shape as they orbit. So every curve you see in that picture there is one orbit of the system. Every 7.93 years. Each one of those represents a 7.93 year orbit of the two stars around each other.
Wow.
And so they're moving outwards very fast, actually. Okay. But every one of those one turn of the spiral every 7.93 years.
Well, is this image that we see, is this an artist rendition, or is this something that
is the actual deal?
They're actually catching that.
Yep, that's infrared light.
So what's
Webb?
Wild. Yeah, this is 2 light years across. Yeah. Is what they're saying in this article.
One end of this spiral structure to the other is about 2 light years across.
Just insanely big.
Insanely big.
This is ridiculous. It's just truly. I mean,
I would love to see a movie of it, and I imagine they're going to do that. That they're going to take a shot of it periodically, once every couple months or something, and then you can put them together, and over the next 10 years, you'd be able to see a little bit of motion, see a little bit of movement as these ripples move out, and a new ripple is created at the middle.
Wow.
So the ones on the outside were created a long time ago. The ones on the inside are fairly recent.
Mm-hmm.
Well, Paul, you have rippled our brains just as well. Thanks for your patience. Thanks for helping us understand a little bit about not only our world, but but like how we think about things. That's the part of science I find so fascinating. Is not just the data details from any particular scientific discovery, but what it makes your brain do to sort of make sense of it all. Like it's another way that human beings describe things. Like there's a lot of other ways to describe, and there's other ways of thinking that we also engage, but this stuff is just fantastic. So thank you.
Thanks for having me on.
Mind blowing. All right,
we'll
buddy.
see you in a couple weeks.
Be nice to those kids today. All right.
I will. Bye.
Okay. All right. I'll tell you. All right. See you, Paul. We're going to keep talking because, you
guys take care.
Okay.
A couple weeks.
That was just the voice in the background. I'll tell you, Dan, this sciencey stuff, I can see why people say like, oh, I'm not into science. Like, I don't get it, because it really is it's an exercise of the thinking, especially the stars and, the big stuff.
Yeah.
The little stuff too is kind of complicated. You get into the, nanotechnology stuff. It's mind blowing. Actually, the medium sized stuff is sort of confusing too. Now that I think about it.
Now that I think about all sizes of things, very crazy.
Yeah, truly something.
Yeah.
All right, is that good for today?
I think so.
Anything else? All right. Well, hey, all. Thanks for being a part of the podcast. I listen to a lot of podcasts. Other people always end it. And live streams and YouTube videos and stuff. Pay attention to a lot of those. People always have invitations for people to do, like send us an email at this note. Click on this thing. See us over there. We always just say goodbye.
Real missed opportunity. We could be begging people to do things.
Well, we'll say thanks to Jim and thanks to I Like to Watch, which is fantastic. Was that a YouTube comment?
Yeah, it's a YouTube. He says,
I like to
you're
watch.
blowing my mind. 2 light years across. Yeah.
Boom. I don't want to get started on my mind blowing today. It was extraordinary. All right. Well, we'll go do whatever it is you were already going to do, good people. And hi, Catherine. Click and like and share and do a thing and send us an email at info@vocommongood.com or I don't know, whatever people
But
say.
definitely drop us a note if you if there's a topic you want us to get into with Astrophysicist Paul Wallace or some other
Totally.
topic, economy, whatever, drop us a note.
By the way, we will be talking, this Thursdays, sometimes we talk science, sometimes we talk economics, sometimes we talk border. So we do move this around. We will be doing a select conversation about the economy as Congress pushes toward not funding past expenditures that they call debt. We will, again, remind you of that. And if you want to go back and listen to any of our previous podcasts or watch the live streams where we've talked with economists, we'd love to have you do that. There's a couple of them on there with Fadl Kaboub, which you'd really love on understanding our economy. And then we did a listening to and a conversation through Stephanie Kelton's book, The Deficit Myth, which will help free up your brain as to what's going on with Congress. And when you hear reporters and other people say things, you're just like, that's just not how it works. Or they're using casual language in a way that's inaccurate. So we will be talking about that in coming weeks. So if you feel like you don't know what's going on with the debt ceiling and all that, we'll explain how so much of that is politicians using that topic to try to accomplish some other ends. And it's not about kids with credit cards not paying the credit card bill. Federal budget is not a credit card bill, for the love. And the number of times that people talk about it like that, just.
Yeah. It's a scare tactic. But we'll get into it. And until then, thanks for watching. Yeah.
Goodbye.
See you later, everybody.
Okay.